Let us talk about kinematics and the equations of constant acceleration. So what does this mean? Well, if we were to plot velocity against time for constant acceleration, it would look like this. For non-constant acceleration, it would be something different, perhaps this. And this, of course, is the sort of trajectory that rockets might perform if they're performing multiple maneuvers. Fundamental to this is the equations of motion, which we will write down as the velocity is equal to the initial velocity plus acceleration times time. We will call that equation 1. And then there is velocity squared, which is equal to the initial velocity squared plus 2as and then there is displacement s is equal to ut plus 1/2 at squared, which we will call equation 3. And these are fundamental to rocketry. Underlying these is Newton's laws of motion. We won't write those down, but it's worth mentioning them. The first law states that any body will continue in a state of uniform motion in a straight line unless acted upon by an external force. So if you have a spacecraft and it's being pushed with some thrust at the beginning and no other forces act on it, it will continue in that direction. So we can think about the Voyager probes, for example, which are outside the solar system, traveling at something like 17 kilometers per second, and they will arrive within the nearest line of sight stars of order 40,000 years or so, unless something acts on them to perturb their velocity or direction. The second law of motion is that when a force acts on a body, the rate of change of momentum is proportional to the force, and the momentum changes in the direction in which the force acts. This is often expressed with Newton's law, second law of force is equal to mass times acceleration. And this is also fundamental to rocketry, because often the force that we are dealing with is actually thrust, measured in newtons, and the mass is the amount of fuel that you may be ejecting from the back of the engine and the rate at which it's been accelerated. Just gives you the thrust. And if you want a rough estimate, for example, what kind of thrust you need to push a spacecraft, you can throw the mass into this equation and what kind of acceleration you're pushing at to give you a rough estimate. And then the third law is that every action has an equal and opposite reaction. And this is pretty useful in things like solar cells, where we know that protons off the sun will be reflected off of a solar cell surface and be reflected back, but they will also impart momentum on the solar cell, and that's fundamental to the force that gives rise to pushing those cells. So let us consider how we might use these equations for a basic interstellar flight kind of problem as a first order analysis. These are what you call back of envelope calculations, because you can literally do these on a beer mat. So the nearest stars are a distance of 4.3 light years, where 1 light year is equal to 9.4605 times by 10 to the 15 meters, and it's the distance that light travels in 1 year. And we're going to assume an acceleration of 1g, which we call g0, which is 9.81 meters per second squared. And let's consider that we're going to accelerate for time for acceleration half a year. So that would be equal to 60 seconds times by 60 minutes times by 24 hours times by 365 days, all divided by 2, because we're looking at half a year, which computes to around 15768,000 seconds. And then we multiply this by our acceleration, 9.81, because we're using this very basic equation here, AT. When we multiply that by 9.81, we end up with a velocity of 154,684080 meters per second. And then if we divide that by the speed of light, 299,792,458 meters per second, we get a value of 0.5159 c, so just over 50% the speed of light. So now we have a velocity and we have an acceleration time, which is half a year. So how long would it take for this spacecraft to get to the nearest stars? Well, we know that velocity is displacement over time. So time, which is our cruise time, is going to be displacement over our velocity. And our displacement is 4.3 light years. This is why we converted it to c. 4.3 light years divided by 0.5159 c. And this gives us a total cruise time of around 8.3 years. And on top of that, we've got to add the time for acceleration, which was half a year. So this is a flyby probe only. So the total time for the mission is going to be 8.83 years. Very simple back of envelope calculation for this problem. Let's ask another basic question. Let's ask, if the spacecraft was to reach 100 AU, at what time in the acceleration profile would this be? So 100 AU is approximately the distance of the solar heliosphere, the edge of our solar system. Both the Voyager 1 and the Voyager 2 probes have now gone past that distance. So we're going to use this equation. We're going to assume a zero initial velocity. So S is equal to 1/2 AT squared. Therefore T is equal to 2S over A, all to the power of a half. Nice and simple, back of envelope. And if we put the numbers in, we end up with 2 times by 100 AU times by 1.496 times by 10 to the 11 meters. That is the definition of 1 AU. All divided by the acceleration rate, which is 9.81 meters per second, all to the power of a half. And this comes out as 174,410.3 seconds. And if we divide that by 60 seconds times by 60 minutes times by 24 days, we get an answer of 20.21 days. So that's when the spacecraft would reach 100 AU distance. Now these equations are nice and simple and good to remember, useful for back of envelope calculations, but it's also useful to know that we can derive them through differential calculus, through their derivatives and integrations. So we know that velocity is equal to the derivative of displacement over time. We also know that acceleration is equal to the derivative of velocity over time, which also means, by definition, these are first order derivatives, but the acceleration is equal to the derivative with respect to time of the displacement with respect to time, which means it's the second order derivative of displacement over time. That's useful to know, and something else that's useful to know and to memorize, because it's fundamental, is this relationship that v dv is equal to a ds, because we often need that to calculate problems. So let's produce one of these laws, for example, by using these derivatives. So let's start off with velocity is equal to the derivative of displacement over time, and we also know that velocity is equal to u plus at. That's our first equation up here. We substitute this into this equation and we get ds by dt is equal to u plus at. And now what we do is we take the dt over. So we've got ds is equal to u plus at dt. And these are essentially integrals. If they are defined with limits, they are definite integrals. If they are not defined with limits, they are indefinite integrals, and we would have to add on a constant at the end. Usually use the terminology plus c to represent that. But we can put limits on to make it fun. So let's start off with the integral of ds between s0 and s is equal to the integral between t0 and t of u plus at dt. So then we have to simply integrate these two terms. So the integral of ds is just s, and so it's s between these limits of s and s0, so it becomes s minus s0. And on the right hand side, the integral of u dt would be ut, and the integral of at dt would be at squared over 2. So we get ut minus plus at squared over 2, and we're assuming here that t0 is 0. We can also assume that s0 is 0, so we can ignore those. So now we've got s equals ut plus 1/2 at squared, and we can see that that is this equation here, derived through the derivatives. Now let's look at another example for these constant acceleration problems. This time we're going to use this relationship v dv is equal to a ds, which is an important relationship to remember. And this is an integral, the way it's written. So v dv is equal to integral of a ds. And we can put in the limits, so this is between s0 and s, and this is between v0 and v. Now the integral of v dv will be v squared over 2, and the integral of a ds will be as. So what we end up with here is basically v squared over 2 between the limits of v0 and v, which is equal to as, which is s0 and s limits, and then we can open up these limits to give us v squared over 2 minus, instead of v0 I'm going to use u squared over 2, which is equal to as minus as0. But let's assume s0 is 0 just to simplify it, and we take over the 2, so we end up with v squared minus u squared equals 2as, and then take over the u squared term, v squared equals u squared plus 2as, and this is one of our foundational equations for constant acceleration. Now these are equations of constant acceleration, and that is how they apply. But what we're interested in also is non-constant acceleration, which is where the acceleration varies with time, in which case the equation is essentially rewritten as a of t, and v squared is equal to u squared plus 2a of t s, and s is equal to ut plus 1/2 a of t squared. So what we're talking about here is a velocity profile, velocity over time, that shows a varying acceleration rather than the constant accelerations we were looking at earlier. So we know that the acceleration is equal to the derivative of the velocity with respect to time, and we also know that v dv is equal to a ds. So these are useful relationships. So if we rewrite this equation here, but now we write the derivative of velocity with respect to time as a function of the acceleration that's changing in time, and we can write that as dv is equal to a of t dt, where we've simply taken the t over to the other side, and this is of course an integral between v0 and v, and this is an integral between t0 and t, and so we can solve these. The integral dv is just v, and the integral of a of dt, but a is a function of time, we leave as an integral because we need to know the exact form of that function, and that depends on the individual circumstances that we're looking at. So we essentially got here v minus v0 equals integral of a of t dt, and we could just put a plus c here if we leave off the limits, or to put it another way, v is equal to v0 plus the integral of a of t dt plus c. And so that's how we would calculate problems, but we'd need to know the exact form of how the acceleration is varying with respect to time, and that would just be substituted into this equation. And just to show another example using this equation, but we're going to consider the variation of acceleration with respect to displacement. So now we can rewrite this equation. Acceleration is equal to v dv by ds, but now rearranging, we have dv by ds is equal to a of s with respect to velocity. So acceleration is changing with respect to displacement based on its position. Rearranging this, we have v dv is equal to a of s ds. This is to be integrated, so this might be between v0 and v, and this might be between whatever limits it is, but it's the acceleration over displacement. So this is very simple to integrate. It's just v squared over 2 v squared over 2 between the limits of v0 and v, which is equal to v squared over 2 minus v0 squared over 2 equals to our integral of a of s ds. And then we'll take the 2 over, and we have v squared minus v0 squared is equal to integral of 2 of a of s ds, or simply v squared is equal to, let's use u squared instead of v0, u squared plus the integral of 2a s ds. And we're going to put a plus c here because it's an indefinite integral. But you can see essentially this is one of the equations of motion, but the only difference is this integral here, which we don't know what the form that is, it depends on the problem, but provided we know that, we can solve whatever kind of weird trajectory that we're dealing with. That's it.